Patterns are all around us. In fact, our eyes and brains are built for detecting patterns. We see patterns even where they don't really exist. Witness the success of optical illusions. We're wired from the ground up to look for patterns and to abstract out the essence of what we see and experience. So what we have to do as teachers is nurture and develop that abstracting ability in our students. In mathematics, we start with concrete patterns, physical shapes and objects that we can give to our students, or even better, get them to make it themselves, and then ask them questions like, how many blocks are there in the third object? What colour and shape will the next piece be? Which number object is this? And most importantly, how would you describe this pattern? As students get better at this, we can start just showing them patterns visually. Keep the physical manipulatives handy for a while though. Even in Year 8 or 9, many students find it easier to understand and explore visual patterns by actually building them with tangible physical objects. Eventually, we'll get to symbolic patterns and even purely numeric ones, with whole numbers or even fractions and decimals. In fact, in the more advanced mathematics courses in senior high school, we even build patterns using algebraic symbols. You might think these patterns look pretty simple, but let me show you where I'm going with this. Let's start with this very simple concrete pattern. How might you describe this pattern? Let's start with the number of blocks in the body and the legs. The smallest shape has 1 block in each. The middle shape has 2 in each, and the largest 3 in each. How many would there be in the next shape, the 4th? How many in the 7th? The 11th? The 32nd? What about the head? Does it change from one shape to the next? Okay, now put it all together. How many blocks are there in each shape? Think that's easy? Try writing it down as a mathematical rule. How many blocks are there in the third shape? Did your rule give you the right number? What about the 4th? The 7th? The 32nd? You see, I can't just use a rule that says add 3 blocks each time. Did I guess right? Was that your rule? It's what most people say. I mean, yes, that's what I'm doing, but it's not descriptive enough and it's not powerful enough. First, descriptive. It doesn't actually say how many blocks to start with for the first shape, the smallest one. Then, powerful. It's very difficult to actually use in practice. I asked you about the 32nd shape. You would have to do this 31 times to use this rule. And yes, I have seen students in this course repeatedly adding to work out these patterns. Let alone trying to work backwards. What's the biggest shape I could build with 80 square blocks? There is a much better way to do this. What is repeated addition? It's multiplication. So let's start with this for our rule instead. The number of blocks I need for the nth shape is 3 times the shape number, n. Well, that's not quite right yet. The first shape, n equals 1, has 7 blocks, but my formula only gives me 3. 3 times 1 is 3. I need another 4 to get the right answer. Let's try it with the second shape, n equals 2. 3 times 2 is 6, plus 4 is 10. Are there 10 blocks in the middle shape? And the third shape, n equals 3. 3 times 3 is 9, plus 4 is 13. Are there 13 blocks in the large shape here? So it's fully descriptive and it's correct. But this new rule is much more powerful. How many blocks in the 32nd shape? 3 times 32 plus 4, which is 100. That was easy and very fast. Or backwards, what's the biggest pattern I can make with 80 blocks? 80 minus 4 is 76, divided by 3 is 25, remainder 1. With 80 blocks, I can build the 25th shape, and I'll have one square block left over. Much better than the first rule. Let's try that again with a different pattern. Here's a simple visual pattern with white squares and black squares. Can you describe this pattern using mathematical language? Can you write a rule that describes the number of squares in each shape? Well, how many white squares are there in the first shape, the second, the third? And how many black squares are there in each shape? Again, we don't want a rule that just says, add 4 squares. It's not descriptive enough. It doesn't tell me how many are in the first shape. And it's certainly not very powerful. It would take me a very long time to work out the number of squares in the 19th shape, let alone the 90th. Instead, let's try building one like we did last time. We're repeatedly adding 4 squares each time. But repeatedly adding is the same as multiplying, so start with that. The number of squares in the nth shape is 4 times n. Well, that's not quite right, is it? 4 times 1 is 4, but there's only 3 squares in the first shape. 4 times 2 is 8, and there's 7 squares in the second shape. I need to subtract 1 from this to get the right number of squares. Let's check it with the third shape. 4 times 3 is 12, minus 1 is 11. Are there 11 squares in the third shape? Yes, there are. Excellent. Now I have a descriptive and powerful mathematical rule to describe this pattern. I can tell you quickly and easily how many squares are in the 19th shape. 4 times 19 minus 1, which is 75. Or the 90th, 4 times 90 minus 1, or 359. Let's try a couple more different patterns. Here's one that's made out of matchsticks, so I'm counting short line pieces instead of squares or blocks. But again, if you give students a pattern like this, make sure you have some short sticks handy for them to manipulate and build with, in case they need to. How many sticks do I need to make the next shape? Well, how many am I adding each time? I'm adding 3 sticks each time, so let's try this. The number of sticks in the nth shape is 3 times n. Does that work? Yes, the first shape has 3 sticks. Yes, the second shape has 6 sticks. This rule doesn't need to be adjusted. Okay, that was too easy. Let's try another. Look carefully. How many sticks am I adding each time to get to the next shape? I'm adding 2. Yes, there's 3 sticks in each triangle, but 1 is shared with the previous triangle. So let's try the number of sticks in the nth shape is 2 times n. Now the first shape has 3 sticks, not 2, and the second shape has 5 sticks, not 4. So I need to add 1 more to my formula. Check it on the third shape. Does it have 7 sticks? Yes, it does. So this rule is correct. 1 more. I'm making little houses. Look carefully. How many sticks am I adding each time? I'm adding 5 each time, not 6. Count carefully. The first house has 6, but everyone after that only adds 5 more. So my rule is going to look like this. The number of sticks in the nth shape equals 5 times n. Now, does that work? Not quite. The first shape needs 6 sticks, so let's add 1. The second shape has 11 sticks, 5 times 2 plus 1. The third has 16, 5 times 3 plus 1. Good.